Hi everyone. In this video, I want to discuss some of the building blocks that you need to learn to build a retrieval augmented generation pipeline or RAG products and applications. One of the most important aspects or applications of large language models has been in creating these products that allow you to chat with your documents. And you can imagine this is very useful if you have documents that are very specific to your task. For example, if you have a collection of research papers that you've collected specifically for your domain of expertise or your domain of study, and you were able to ask questions and get responses across different types of queries. For example, you could ask for a summary of a particular research paper. You may even ask for a comparative study across various research papers for a specific experiment. I think the possibilities are endless, but building these can be a bit tricky. And I think if you know how to code Python, you should be able to do this in probably a day or two, even less if you are more proficient in Python programming. So in this video, I want to showcase some of the building blocks that you could use. Of course, if you're aware of this field, there are a lot of great libraries out there like LangChain and Llama Index that abstract away a lot of the building blocks that I'm going to talk about here today. So you feel free to use those libraries. Here, I want to talk about, maybe look under the hood and understand how some of these are put together. Sometimes you may want to just learn it for going a bit deeper into the subject. And for, I think, students who are in college, this would be great material to, take and go back, try things out, and really get a sense of what's going on with retrieval augmented generation pipelines. The first step is obviously to find an interesting knowledge source. I think you could start with PDF collection. Any PDF file should do. Maybe you can find a couple of documents. I've also shared a couple of document collections on Kaggle. One is a collection of AWS case studies. The other one is a collection of 200 plus research papers that I downloaded from archive in the related to large language models and NLP. So you could use either of those. After that, there are a couple of steps to extract information from that PDF document, chunk it, make it sort of smaller than the certain size, store it in a SQLite database. Maybe you could use it for full text search, extract embeddings or vector representations of those pieces of text, and then store it into a vector index for vector search. Finally, integrate a query, a response from your database, and send it to a large language model to get a response. Now, these are the different building blocks that I mentioned, and how they work together is described in this diagram. On the top right, you can assume that you have a knowledge source, a collection of PDF documents that you're going to process and make it available for your retrieval process, right? Once you have extracted the information, stored it in an appropriate manner, like I mentioned, stored it in a way that you could do a text search or a vector search, then you're ready to receive a query, which will then be be an input to your retrieval system. So once you have a query and you already have your PDFs converted to the data structure that I mentioned, you will retrieve relevant chunks or relevant pieces of information from that database. And along with the query, those pieces of information, you will create a prompt that will be sent to the large language model. And the response will be what you can imagine if you've used ChatGPT. It will be a response that is very coherent, very engaging, and will summarize a lot of the content that you have retrieved and sent to as part of the prompt. So the first step obviously is to process the document collection that you already identified. And in this piece of code, you can see that we've identified the directory where the PDF files are stored. And we use a very popular library called fits or new PDF. What it's doing here is it's going file by file, and within each file, line by line, sorry, page by page, and then extracting the text on that page. Okay. Now, there is a link in the video description for the actual material that you can find here. In this material, you will learn a lot more about what's going on other than just the piece of text or the code. I've described where you can find the input dataset and how do you install the necessary libraries. And you can also look at more information around what's going on once the text is retrieved from the PDF file. Once you have the text from each page, there's a reason you chunk up the text. Well, this goes into a bit more around embedding models and their context size. I think you should, obviously do some research on this area, because if you're interested in just building AI applications, RAG pipelines, knowing the context length for embedding models is very important. Of course, these models are becoming more and more adept at extracting embeddings from large uh, context lengths, but typically you also want to have a trade-off where the chunk size is appropriately chosen, and it's more of being able to tune that. So once we have the text from every page, we want to chunk it up into maybe 400, 500 words, right, or maybe a couple of paragraphs. This is done because when you're retrieving content at the time of querying, at the time of receiving a query, if your chunk is as large as a page, you will end up sending a lot of information in the prompt to the large language model. And this could have other effects like increasing your costs if you're using a commercial API or using GPT-4. It may also reduce the quality of the output. And some of these trade-offs are best judged by the specific application you're trying to build and by experimenting. So I've used chunk size 400. You could use another number. You could completely use a different text splitter, from LangChain. There are many available, and I've provided a link to that. So ensure that you're going through some of this information and trying to really build your own understanding. You could then store that information that you've extracted, the chunks from those PDF files and pages, into a SQLite database. This is because I'll show you how you could do full text search with SQLite. And it's a very simple, table structure. Storing the chunk ID, a chunk text, page number, the document PDF file name, right? And once that is done, you can go to the next step. But before we go to the next step, I think it's important for folks who aren't aware of SQLite to really spend time and learn about this amazing database. It's literally everywhere. It runs on your phone, your browser, and there are places where it runs that I don't even know about. It's everywhere, really, and it has great support for almost all features that you might find in a full-fledged database. There are, of course, some trade-offs in using SQLite. It's not useful if you have a lot of writes coming in, where your database keeps getting updated in a concurrent fashion. But it's very useful for a read-heavy application. All right, so let's go back to our table of contents and then look at search with SQLite. So I think we've covered a large amount of context around finding PDF documents, processing it, extracting text, chunking it up, and storing it in a SQLite database. Once you have this information, let's say you want to um, just try text search. You want to provide a few keywords and you want the right information or relevant pieces of information being retrieved. In SQLite, there is a feature called full text search, which you can easily use. I've provided some information on how to do that here. Once you follow these instructions, you'll have the ability to issue a query that looks like this, right? Of course, you can have multiple keywords here. I'm just using one, for example, but you're able to match a query that has a couple of keywords along with the data that's in SQLite. The next step is to consider nearest neighbors, right? When I talk about nearest neighbors, there's a lot of, I think, context that you have to gain, and some of these articles here on uh, text embeddings is useful. So there are two aspects here, right? You can apply the nearest neighbor algorithm on a data set that includes embeddings extracted from text, or it may just include tabular data. It may be a data set of, let's say, information regarding sales across different products. That would also include various information around what that product is, how many reviews it's received on the website, what category it belongs to, its price, reviews, and so on. Now, that's a lot of information that you could use as features to apply the nearest neighbor algorithm. And really, what the nearest neighbor algorithm is doing is it's taking an input, let's say an input row from your data set, and identifying other rows in your data set that are similar, right? And the similarity is based on a function that takes in the input row, or let's say all the elements in the input row, and compares it with all the other rows in the data set. And the comparison is based on every feature or every column being compared to the equivalent column in rest of the rows. You could use Euclidean distance and other distance metrics to identify how far is the input row from other rows in the data set. And when this approach is applied to text, identifying a numeric representation on text has been something that researchers have been working on for a couple of decades or more. Today, what we have are these embeddings that are trained on large amounts of data by companies like Twitter, Google, Facebook. A lot of people are also sharing these embeddings that are trained on large amounts of data so that anybody could use it to featureize a piece of text. And I think, I will go into more details about this in another video, but today you could read some of these articles and learn more. And I think there's many libraries. A lot of work has been done here. And if you go to Hugging Face and search for sentence transformers, you'll find a ton of models that are made available. I'm using one, but there's a leaderboard. I've linked to it where you can identify another embedding model that you could use for your project. And I would say it's always very useful to go and experiment with some of this. And the rest of it is very simple. I think you have your data set, you can extract the embeddings, and then you create this nearest neighbor algorithm, or you apply it to your data, and then you could sort of issue, like an input query in the form of a vector. So your input query comes in, you convert it using the embedding model, just like you did for the information shared stored in your data set. And then you're able to retrieve the nearest neighbors. And you can see the outputs are actually not available here. I'm going to share a link to the Kaggle notebook. You can find it in the description, or you can find it in the table of contents. And that Kaggle notebook has all of these pieces of code executed with outputs that you could look at. Now, what I'm trying to show here is that nearest neighbors, vector search, they're all not very difficult concepts to wrap your head around, right? If you find it difficult, I think it's mostly because you may not have spent some time on understanding some of the basics. And if you look at embeddings, vectorization of text, you'll get a good sense of what's going on here, right? Now, I think the next step is how do I take vectors, or how do I take embedding vectors across thousands and millions of pieces of text, and then do what I did earlier, find nearest neighbors, right? When you're looking to scale up, you might end up with challenges in the previous approach where we use the scikit-learn k nearest neighbor algorithm, and which is why there's a lot of solutions out there. Annoy is a library from Spotify, and this came out a few years ago, where if you store a large number of vectors, you can do things like vector search. And storing the large number of vectors is done in a more efficient manner so that when you're retrieving or doing the vector search, you're not comparing that input vector across all the vectors in the index. You're doing it in a more efficient and a smarter way. And I invite you to read more about the library and how it has been implemented. And the great thing is today with large language models and RAG pipelines being so popular, you'll easily find a lot of information around vector databases, vector search out there. There's a lot happening in that field. Almost every week, I see a new database that supports vectors, and or is a vector first database, and a lot of existing database uh, projects, open source and commercial, are supporting vectors as a feature. So you can imagine how important this field is for building RAG products. Here, what you will notice is that I'm showing you how to use Annoy, but some of the previous steps remain the same. We extract vector embeddings from the chunks of text that we've already stored in the SQLite database, and we create a vector index using Annoy. And once you have the vector index, all you have to do is receive a query, convert it to a vector embedding using the same model with which you converted your text that was in the database, and issue the vector search command. And you'll see output that is similar to your query. I've already tried this in the Kaggle notebook, and you can too. The next step is really, we're taking a pause before we go to large language model integration, because what I want to showcase to you is, while we are building all of this, it becomes very important to maybe deploy this in your maybe class project or at work. And two important technologies that I think are important because one, Fast API lets you build a web service around whatever it is that you've developed, right? In this case, let's say you have a web service where a client can make a call, send you a piece of text, a query, and receive a large language model result. And once the web service receives the result, receives the query, your the code that you've written gets to work and then sends back the response, right? And you can build that uh, with using Fast API, right? Docker really is useful because you can containerize the application. What that really means is you have an environment that is built or purpose built for the application to run, your Fast API service, the other pieces of code that you've written, where you may need the Annoy library, you may need scikit-learn, and Docker allows you to create an environment where all these libraries and dependencies are available. And platforms today across the world, across providers like Google Cloud, Amazon Web Services, support containers being deployed. So you could just deploy that container directly, or your container image, or you could get yourself a, let's say, system compute instance in the cloud, let's say EC2, and then just install Docker and run your image, run your container there. So knowing Fast API is very useful to build applications that can run in an environment where anybody could make a call and use the feature that you built. And Docker makes deployments very easy. It makes it makes it easy to build environments so that you could run it on any cloud as long as it support containers, and almost every cloud supports containers directly. Or you can just get yourself a compute capacity online and then install Docker and run your image. It will be as simple as that. And I think finally, what I'm trying to show in this piece is how do you convert all that you've done into a prompt to a large language model. So before we continue, let's take a step back, right? We've come very far in this journey. We had a bunch of PDF documents. We extracted text. We chunked it up. We stored it in SQLite where we could do keyword search. We also converted that text chunks into vector embeddings and stored that in an ANOI index, which would allow us to do vector search. And now what we're going to do is how do we take all of this and build a integration with a large language model? And in this case, I'm using OpenAI's GPT-4 or GPT 3.5, and the steps remain the same, right? I receive a query, I convert it to a vector embedding, I issue that vector as a search input to ANOI. I receive all the nearest neighbors or approximate nearest neighbors, and then I use that information to extract the text that is mapped to those IDs of those vectors, and then I use a template that looks like this, right? So this is the template that is going to be used to assimilate the information that I received both from the user, which is the query string, and by retrieving chunks of text from my ANOI index and my SQLite database. And basically, here is where I will provide the chunks of text that I retrieve, and this will be the query. But it's more important to understand that to the LLM, I'm going to send this prompt, right? So this will be, the first line in the prompt that goes to the LLM. This piece will get replaced with all the chunks that I receive that are relevant to the query. The prompt is asking or instructing the LLM to say to use only the information that's in the context and not its prior knowledge. And that's very important because what we are trying to do is have the LLM use the information that we have sent and then respond back in a very engaging and synthesize that information in a very clear, concise manner that we are all used to as we have experienced ChatGPT. And the query obviously is the query that you want a response for. And then you're basically making a call to OpenAI. And by the way, this prompt was taken from the Llama index library. They have a lot of prompts or prompt templates that are very useful for you to check out. Once you have gone through those steps, you're basically making the call to the LLM and receiving a response. And again, the Kaggle notebook can be cloned, and I've linked to it in this document. You could actually check it out here, right? And once you check this Kaggle notebook out, you could clone it, you could try to run those steps by yourself, and then you get to a point where you build an entire RAG application into it. In other videos, I'm more than happy to go into or deep dive into specific areas. So leave comments, subscribe. These are going to be videos that I'm going to be putting together. It's first time doing it, so your encouragement, feedback is very, very, very appreciated. Thanks for listening, guys, and have a good day.